Hyperconjugation effect, acidity, basicity of organic compounds, which itself is a very vast topic, right? Reaction intermediates. So we have to decide how much we can do in today's class and what all we'll be able to complete when. So today we'll complete aromaticity, resonance, inductive, hyperconjugation effects, okay? And just electrophile nucleophile introduction. That part we'll complete today. Tomorrow we'll do hydrogen bonding effects, okay? Once we'll do that, and these all intermediates. ठीक? As I could see, tautomerism is also part of this week. So we'll do that. One class we'll give to acidity basicity. That is 3. Fourth class we'll go for chemistry in everyday life. And if required, then tautomerism somewhere we'll do. Right? I request you all to kindly keep yourself on mute. Okay. Yeah. Please keep yourself on mute. And if you want to speak anything, then only you unmute yourself and can ask doubts. Okay. Till then, please keep yourself on mute. And do not do any time waste process in the meeting in between. Otherwise, it would be difficult not only to complete the syllabus, but to keep you in the meeting for every class, right? There are people who are watching and the meeting is recorded. It will be recorded who has done what. So let's start. As we have seen, it is a class for GOC. Now, GOC is General Organic Chemistry, right? In this, we will, of course, start with electronic effects. Now, electronic effects, if we see, so any such effect which is generated due to movement of electrons, these are called electronic effects. They could be temporary or permanent. ये दोनों ही तरह के हो सकते हैं. There is a possibility that it could be temporary or it could be permanent. Both type of effects are possible, right? So दोनों ही तरह के इफेक्ट हमें देखने को मिलेंगे कि टेम्पररी भी हो सकते हैं और परमानेंट भी हो सकते हैं. अब ये जो दो तरह के इफेक्ट है कि इट कुड बी टेम्पररी और परमानेंट, एज पर our syllabus, if we talk, then temporary effect is like electromeric effect and permanent is like inductive, resonance, hyperconjugation, aromaticity, steric inhibition of resonance, and like that other effects. If I talk of electromeric effect, though I will also cover, but will strongly recommend you to read for electromeric effect because the best and the only source for this is NCERT 11th Basic Concepts chapter. Please read it, and there is something which can be converted as such into any type of objective question that we can expect in mains or advance. Okay, so coming to the permanent effects which are part of our syllabus is first inductive effect. We will not go much into detailed theory, but we'll go for the important points. So what is inductive effect? Inductive effect is polarization of a non-polar bond due to presence of polar bond in the vicinity is called inductive effect. It is permanent effect. Okay. Now, how it is defined? Like we said, it is basically polarization of a non-polar bond. So we say that CH3, CH2, Cl. Due to polarization of this bond, del plus, del minus, this bond which we were expecting to be non-polarized because both were carbon sp3 hybridized is now having a del plus polarity, right? Or if I could say further del plus polarity as the electrons are pulled towards chlorine. Okay, so such polarization of a non-polar bond due to presence of a polar bond in the vicinity is called inductive effect, and the word is from induced effect. This polarity between CH3 CH2 is induced due to a polar bond CH2Cl, so it is called inductive effect. Now we have divided into two categories. One is the plus I group, one is the minus I group. But how these plus I and minus I were devised? So they took reference of carbon hydrogen bond. In a carbon hydrogen bond, assume this is the lone pair position. Then they took whatever group they want to study. If with respect to this CH bond shared pair position, it is found that electron pair is more towards G, then we'll say, okay, this G is a minus I group because it is attracting the electron pair towards itself. And in this process, this G will ultimately acquire a del negative polarity, generating del plus on the carbon. So what is the reference frame taken? Carbon hydrogen bond is the reference frame taken. With reference to CH bond, we define minus I and plus I. Now, how about plus I? In case of plus I, they do the same thing. And if that lone pair is more towards carbon, with compared to the CH bond shared pair, if that lone pair is that shared pair, now here, this carbon will acquire del minus and G will acquire del plus, and this G is now said to be plus I group as it is pushing the electron pair away from it. Okay, so when it is pushing the electron pair away from it, then we call it a plus I group, and when it is towards the group, then it is called a minus I group. Clear? Now, we have to have an order. And this order, I want all of you to almost keep in memory. Okay? हमेशा इसको थोड़ा याद ही रखना पड़ेगा. May not be each and everything, but जितना आप याद रख पाएं, you have to memorize this order. So plus I order, सबसे अच्छा O minus, then CO minus, then CR3. CR3 को आप 3 डिग्री अल्काइल के नाम से भी जानते हैं. ठीक, CHR2 इसको we can call 2 डिग्री अल्काइल. CHR2 is 1 degree alkyl, and so on. It's CD3, then CH3, then deuterium. See, deuterium, if compared to hydrogen, is acting as a plus I group. Matlab, it is giving electron towards carbon. The reference is CH. Otherwise, it is not such a strong plus I. But for comparison, the reference is CH. With that comparison, it is a plus I group. Order of minus I groups, if we talk, very strong that you have to remember is NF3 plus. Now see, when I talk of NF3 plus, the plus polarity is coming on this nitrogen. Okay, so definitely if you ever have to compare and you have got OP plus, in case if you come across something like this, then definitely it will be even stronger minus I group, because an electronegative atom having a formal charge of positive is acting as a strong minus I group. Is that clear? Then comes the NF3 plus, NR3 plus, then SR2 plus, and then NH3 plus. See, R is there, but the R acting as a hydrophobic. Okay, overall hydrophobic है R. As a result, this overall cannot let water come close to N plus. Cannot let water come close. I mean, what happens that when water is surrounding this NR3 plus or NH3 plus, the negative pole of this oxygen right? Neutralizes the plus polarity of nitrogen plus. But in Nr3 plus, due to hydrophobic nature of R, this is not possible. This attraction does not take place. Water could not come very close to N plus. Okay, so as a result, the neutralization of plus polarity of nitrogen could not be achieved to the extent at which we can have such neutralization in NH3 plus, as hydrogens themselves will participate with NH bonding with water, and more water can approach, can come close to NH3 plus, and thus the plus polarity of NH3 plus will be neutralized to a certain extent. Okay, and thereby its plus polarity decreased, less ho gayi hai. If it is decreased, it will be less minus I. Therefore, NH3 plus is a less minus I group than NR3 plus. Then comes the nitro, SO2R, cyno, SO2AR. AR matlab aryl, C6H5 you can put in place of AR. Okay. Then comes the COH, fluorine, chlorine, bromine, iodine. OAR, COR, OR, aldehyde, ketone, SHOH. Then comes the hydrocarbon part. These three are easily explainable, right? This is sp hybridized group. Here it is sp2. This is also sp2. But in phenyl sp2, there will be further certain groups, right? Further carbons are there which can cause extra minus I. Is that absolutely okay? Which can cause extra minus I. And therefore, it is a stronger minus I group than simply CH double bond CH2. Is that clear? I hope this is understandable. If there is anything doubtful, you can either raise hand or can drop a message in a chat box. Either I will be able to see now or will see in the end. Okay. So this is how the minus I order is. But ye minus I order, this minus I order, you need to keep in your memory. And the only way for that is please write on paper 2-3 times without seeing the without seeing these slides or without seeing your page. Okay, then only you will be able to remember that. CLF. Okay. Moving further, now there is something about the rules of inductive effect that you need to keep in your memory. Inductive effect decreases with increase in distance from the source. Inductive effect is always compulsorily inversely related to distance. As we have just seen, chlorine acting as a minus I group. Far away we go from chlorine, and more far away we go from chlorine, it will become more and more difficult to execute the minus I of that group. Okay, so practically जितना हम दूर जाते हैं, more the distance from the source atom or the source group, less will be the minus I of this particular or whichever particular group is consideration. If the distance is maintained same, okay, this point is applicable only when distance is same. Most important factor is distance. If the distance is same and there is a comparison between number and power, okay, then always number dominates. Whether the group is weaker, whether the group is stronger, okay, between number and power, it is always what dominates? Number dominates. See, these are the examples. Let us first compare. Inductive effect decreases with distance example. First, let us see. How will you compare that distance factor? So, you see, we have to compare the effect on this C. From here, if I say 1 sigma bond, and next I am finding the CCl bond at a distance of 1 sigma. Here, 1 and 2 sigma. Now you are having this bond. So distance is more. Minus I will be less. And we are talking of carbocation. So less minus I is making it more stable. Okay. So you simply count from the source and the effect, where you have to check the effect. How many sigma bonds you are away. Practically, if I talk, okay, not for questions, practically we ignore I effect from 3 bond, 3 sigma bond distance and onwards. Distance and onwards. But that is again, please keep in mind, practically I am saying. Okay, आप ये काम practically कर सकते हैं, but if there is a question that one has a group and one do not have a group, then you will not talk of कि it is far away or it is close. You simply say one is having and not having, then go for direct comparisons as we were doing. Okay, coming to point number 2, in between number and power, always number is the winner provided the distance is same. As I said, how will you check the distance? So C plus is the center in question. From there, I check 1 sigma. Then I have the next CNR3 plus bond. Okay. C 1 sigma. And then I will have, now you may get confused if I write it this way. But if I write it like this, that it is CCl, Cl and Cl. See, it is very apparent that after 1 sigma, you have the minus I sigma bond, the bond which is exerting the minus I or will induce the effect on our bond. Similarly, after 1 sigma, there is a CCl bond which will induce the effect on this C plus bond. Correct. So when I talk of these things, talking this Cl or this CNR3 plus. Okay. So distance is same. And when the distance is same, you can see there are 3 chlorine. There are 3 bonds here, whereas only 1 NR3 plus here. Here we have only 1 NR3 plus bond. Here we have 3 CCl bonds. So I think you have got the point. So 3 Cl bonds. So I would write stronger minus I. It will exert a stronger minus I than this. And we wanted to compare the stability of carbocation, less minus I better. So this is more stable. Okay. So this is how you can use the distance same, then number and power into comparison. If the question is that distance is also changing, number is also changing, power is also changing, then the only thing you will consider for comparison is distance. More the distance, less the inductive effect. That is the most important criteria for inductive effect. Okay. And a very important definition wise also you must be remembering, or I should add, it operates only through sigma bond, right? Inductive effect do not affect or do not operate through pi bond. It always operates through sigma bond. Next, we are coming to resonance. Now, resonance is also known as delocalization of pi electrons. Yes, it is a hypothetical effect. Okay, there is no practical evidence, or we have never seen it happening. And all the resonating structures that we draw are imaginary. All the resonating structures are imaginary. The only real entity is resonance hybrid. Okay. Now, how the resonance came into scene? As we could not explain resonance hybrid by our limited chemical bonding knowledge till date, and thereby we took help of this resonance theory and draw resonance structure and say that hybrid is a sort of combination of all the resonating structures. All resonating structures coming together will give you resonance hybrid. Okay. In writing resonance structures, we are allowed to move only pi electrons, not the sigma electrons, not the एटम. किसी भी एटम को हम मूव नहीं करेंगे, किसी पाई बॉन्ड को मूव, किसी सिग्मा बॉन्ड को मूव नहीं करेंगे. वी विल ओनली एंड ओनली अलाउड टू मूव पाई इलेक्ट्रॉन्स. ठीक. Sigma bond we will not delocalize in resonance. All resonating structures must have same number of unpaired electrons. There should not be, like, what I want to say is, as resonance is a theory, is an imagination, but an imagination will be accepted by other scientists or the scientific world only when it is able to explain real phenomena, right? It is not possible that you speak any random lie and will be accepted. It is how realistically you can present your theory. So, why this point is important, that should have a same number of unpaired electrons. This point is important because see, CH2 double bond CH, single bond CH, double bond CH2. If I want to draw its resonating structures at CH2 plus CH double bond CH and CH2 minus, and if I say I want to draw CH and then CH2 dot. Now see, in these two structures, the number of unpaired electron is 0. Okay, yahan number of unpaired electron is 0. Whereas in these two structures, number of unpaired electron is 2. So definitely this will have some paramagnetic nature and these will give a diamagnetic nature. But there has to be something fixed behavior that a hybrid is exhibiting. And if the hybrid is exhibiting a clear and a direct observation that this 1,3-butadiene is behaving as a diamagnetic, then we cannot have these structures. So that is why, because if you change number of unpaired electrons from one resonating structure to another, then what you are doing is you are fluctuating the behavior between the actual observed diamagnetism and paramagnetism. So your presentation or your resonating structures should be in sync with what is being observed as a diamagnetic or a paramagnetic nature of the molecule. Okay, coming to point number 5, all atoms that are part of delocalized, part of delocalized electron system must lie in a plane or nearly planar. Please write short notes wherever you want anything. Okay, I am going quite slow. You can have writing short notes. Le sakte. Okay, all atoms that are delocalized, we just want that part of the molecule which is part of delocalized electron system to be planar. We don't want entire molecule to be planar. This is something that has to be very clearly placed in your brain. Okay. So what I want to say is, for example, I have CH3, CH double bond, CH single bond, CH double bond, CH2. Right. So my resonating part is only this. So I'm not bothered about iska sp3 nature. Right. If I want to talk of CH3, I'm not bothered about this CH3. The part which is in resonance is planar. Clear? So only the part which will participate in resonance has to be planar, not the entire molecule. We do not want the entire molecule to be planar. The energy of the actual molecule is always lower than energy of that might be estimated for any contributing structure, always, because resonance energy is a stabilizing energy and is conventionally written with negative sign. It is always written with negative sign. Now, why it is lower? Because whichever resonating structure you draw, it is going to be a fixed location, fixed set of bonds. You will draw Lewis dot structure only, in which the bonds are fixed, in which the electrons are localized. So the potential energy of that resonating structure is always higher. Whenever things are fixed, whenever electrons are locked at certain position, fixed at certain position, repulsions are generated and the potential energy becomes higher. Whereas hybrid, in which those electron densities are diffused, so repulsions are always less, and thus the hybrid is always more stable than any of the resonating structure. Whichever you draw is always going to be less stable. Coming to point number 7. Equivalent resonating structures make equal contribution to the resonance hybrid, and a system described by them has a larger resonance stabilization. Yes, this point is by and large true, but I would like to add something in this point. Okay. Whenever you are comparing the resonance energy of two different molecules, okay, two different molecules. Now, when I talk of two different molecules, then it is entirely different story. Say, for example, if I have CH2 double bond CH single bond CH2 minus, then I have, say, CH3 CO minus, and I have PHO minus. Okay, let me erase it and draw again. Yeah. So what I wanted to say by this thing of equivalent resonating structure. Now see, if I draw, this has equivalent resonating structure. There are only two resonating structure and both are identical. Okay. This has exactly equivalent resonating structure. Fine. Now this does not have equivalent resonating structure for sure. Right? You will draw something like this, and then you will draw minus, and going further, you will bring minus here and one more O minus, right? So you have overall got 5 resonating structure, 2 resonating structure, 2 resonating structure. Now, by the sheer logic of equivalent resonating structures are more stable, yeah, have more resonance energy, right? Equal contribution to the resonance, and a system described by them has a larger resonance stabilization. Resonance stabilization indicate the word resonance energy. That is inadequate terminology, I would say, because if I'm asked here, I'll say most stable. If I call them as 1, 2, and 3. Certainly 2 is the one which has the best resonance energy and is most stable. Then it is 3 and then it is 1. Despite equivalent RS. So how to solve then? Okay, so for comparing the resonance between molecules, always as a rule, first check who is the charge bearer. Okay, that is the most important factor, that who is involved in sharing the charge. Then how many of those? Okay, second thing you will consider is how many of those. First is who is participating in resonance, then you think of how many. So what is happening that here, who is the charge bearer? C minus and C minus. 1C minus 2C. Here O minus and O minus. Here C minus 4 times and 1 O minus. Okay. So of course 2 oxygen minus sharing equally best 1 oxygen minus versus 4 carbons. So carbons still are there, but 1 oxygen will support and delocalize the charge better than the 2 carbons. Okay, so this is more stable. So अगर आप में से कोई हिंदी जान रहा है तो I'll write पहले कौन फिर कितने. And if you are not understanding Hindi, then you write that first you have to check who, then how many. Okay. First question you need to ask while comparing the stability or resonance energy of the two molecules is who is the charge bearer. Then you ask how many such atoms are there. Coming back to what we were doing. So this entire explanation was for 7th point. Okay. Coming back here, the more stable a structure is when taken by itself, the greater is its contribution towards the resonance hybrid. More stable structures contribute better, contribute larger percentage towards the hybrid. They will dominate. Now, what do we mean by that they will dominate? We simply mean that they will affect the properties of the molecule to larger extent than any other structure. So you will have more number of behaviors or property of that molecule as compared to others. Okay, moving to next point. See what type of questions appeared on this concept. First, see the number of resonance structure. This type of question could appear for N. So phenol react with NaOH. So you will have acid-base reaction and phenoxide is formed. Okay. Now this phenoxide can resonate as we have just drew the structure 2 pages back. So I'm rushing directly. Double bond O minus, again double bond O minus, like this, and O minus. So we have got 5 resonating structures. Okay, so answer for this is 5. On the same line of thought, in 2015 advanced, the number of resonance structure for N, yahan par puche, in this particular structure. Okay, I want all of you to do it in your notebooks. Maybe after the class you can try. Answer for this question is 9. You will get 9 resonating structures for the anion that will be formed after this reaction. Okay, so please do this question on the same lines. As you all are in phase 2, so I assume all of you are good in drawing resonating structures, how to draw the resonance structures. Now, we have seen that two molecules, let's see, coming back here. Here we were comparing all resonating, in writing resonance structures, we are allowed to move pi electron. And then we started comparing the resonating structures stability, okay, and how they were affecting the resonance energy. Moving further in that direction, if for a same molecule, I compare the stability of different resonating structures, okay, for a same molecule. So the most important first factor, the more the number of covalent bonds a structure has, the more stable it is. More number of covalent bonds. See here, you have sigma. If I leave, sigma will remain fixed. So I leave 1 pi, 2 pi. So here I have 2 pi bonds. Whereas if I come here, I have only 1 pi bond. Other is broken and is converted into charge. Same here, 1 pi bond. So more number of pi bond, you can call it that this is more stable. Okay? The same thing is also referred as neutral structures will be more stable than charged structures. Certainly, because neutral structures will definitely have more number of pi bonds if they are converted to charge, unse compare karen to. Okay, so neutral structures are more stable than charged structures. Okay, neutral are more stable than charged structures. Going to next, structure in which all of the atoms have a complete valency shell. This is again the same idea representation. See, more completion of the valency shell, it is ultimately having more number of pi bond. Okay, but this point is very, very important because these two questions have been asked in advanced also and in mains also. This one is from mains, this one is from advanced. So the concept, of course, now R I am keeping variable. So if you are seeing this acylium ion, this is resonating structure, then I take lone pair, triple bond is formed, O positive. So 2 is more stable than 1. 2 is more stable than 1. This is very important. I don't know how emphatically I am able to communicate. Please remember, this structure is very stable, even more stable than any 3-degree carbocation. Coming here, see this oxygen, okay, if it gives bond like this, so it can have a resonating structure. CH3CH double bond O CH3 positive. Yes, you are seeing an electronegative oxygen with a plus charge, but when the octets are complete, such positive charges are welcomed, are allowed. Whereas here, I can certainly not use this charge. Right? I cannot use this type of charge to stabilize my plus. 2 sigma ka distance is there. So this cannot have resonance. This is having only minus I of OH. Whereas here oxygen is giving certainly minus I but giving plus R also. So this is more stable. 1 is more stable than 2. If charge separation is considered, more the charge separation, okay, more the charge separation, you will find unstable, destabilizing effect on a resonating structure. Because what happens when you convert a neutral bond into charges, a work is done on that particular molecule. And when a work is done on that particular molecule, definitely potential energy of that molecule is increased. If the potential energy is increased, then that structure is becoming unstable because its energy is increasing. So if a charge separation is done, then there will be decrease in the stability. Okay, there will be decrease in stability. we'll do its example. But when I say these things that you are able to use, kindly keep a note of uh, when you draw structures, you should know which lone pair you are able to use, which you are not able to use. For example, if I use here NH, I keep here double bond, I keep here double bond, and a plus charge here. Yes, it is a case of cross conjugation. It can resonate this side, it can resonate that side, but still I can use this nitrogen to complete the octet. But in case if the same molecule has been given as plus here, now I cannot use this resonance. 2 sigma distance is breaking the conjugation, and so this is more stable than this. Clear? If further I had say NH2 double bond, 2 sigma are there, and it is a case of continuous conjugation, then this is the most stable. If I say this is 1, this is 2, and this is 3, then if I am asked for stability, I will say 3 is more stable. Why? Because the number of bonds involved are same, atom involved is same, but a continuous flow of electron will be more stabilizing, molecular orbital overlaps will be better, and then comes the 2 least because it cannot use this resonance. Right? What is this? This I am using the term continuous conjugation or resonance. And here I will use the term cross conjugation. Cross conjugation, provided the number of electrons involved, number of atoms involved, type of atom involved are same, then always continuous conjugation is better than cross conjugation. Okay, moving further, draw a resonance structure of the following compounds and arrange them in decreasing order of stability. If you people have registers, please draw it. It is extremely important question. If you have any rough notebook or anything with you, please draw. Don't look at the screen. Meanwhile, I will also draw, and then you check. Hai? You have to also arrange them in decreasing order of stability. So I'll draw, you draw in your notes. Diazomethane. Once you're done, you can check. These are the 4 resonating structures. 1, 2, 3, and 4. And I think only 4 resonating structures are there. Okay. Now, out of these 4 resonating structures, you should select first those in which there is no incomplete octet. See, this plus on carbon, incomplete octet, nitrogen pe plus, incomplete octet. These are going to be the least stable ones. So, by that logic, that octet should be complete. And by the logic, more number of pi bonds. See, 2 pi bonds, 2 pi bonds, 2 pi bond, 1 pi bond, 1 pi bond. So these are more stable. So what we could say, 1, 2 is going to be more stable than 3, 4. That is first thing. Amongst 1, 2, how will we decide? Now nitrogen plus is fixed. Nitrogen minus and C minus is the point of difference. Electronegative bearing negative is better, so 2 is better than 1. Right? Nitrogen pair negative is more stable than C negative. Coming here, just reverse. C plus is more stable than N plus. Rather, I should say like this. This is very, very unstable. But yes, what we could assign, see how the resonance will work for diazomethane. What are the behaviors diazomethane we can say? It can act as base. Yes, very much. बिल्कुल possible है. And if I write this, I think all of you will remember the reaction. This ultimately forms CH3Cl liberating nitrogen gas. ठीक? So in this, what happens? First step is attracting H plus. And then N2 being a good living group. It can act as nucleophile. Very, very much. Yes. And you remember that reaction called earned Estert reaction. Right? Acid chlorides react with diazomethane, forming an acid with 1 carbon up. That is earned Estert reaction. And there it acts as a nucleophile. Then coming next, after earned Estert, we can call that diazomethane. It can act as 1,3 dipolar ion. Right? जैसे ओजोन करता है. See, 1 plus 1 minus 1 plus 1 minus. So from position 1 and 3, it can act as a dipolar species. Yes. D, it can from this structure, or rather from this structure, I can say that nitrogen is such a good living group. And if this happens, CH2 minus and this plus charge, so I'll have a carbene. It can act as source of carbene on heating. If you heat it, nitrogen will go away and you can get a carbene. So diazomethane in itself is an entire chapter, and its varied behaviors are explained by all these resonating structures. Is that okay? So moving further by the same logic, you see now this one, 1-methoxy 1,3-butadiene, CH3O 1,3-butadiene, 1, 2, 3, 4. Again, do the same thing. Draw resonating structures and we'll do the comparisons. So CH3O, CH minus, CH double bond, CH2 plus. I can have so many structures. It is not just this. I'm just discussing few important factors. CH plus, CH double bond, CH2 minus, right? I can have resonating structures in which CH minus, double bond, CH double bond, CH and CH2 minus is there, right? Here, if I give lone pair here, you will get this structure. And yes, you can have a structure in which you polarize only one bond, or CH double bond, CH single bond, CH minus, CH2 plus. Okay, but first I'm mainly concerned about these 1, 2, 3, and 4. Okay, anyhow, 1 is going to be most stable. Why? Because it is neutral. It is having more number of pi bonds. You can say 1 and 4 have same number of pi bonds. Yes, and therefore next is 4. But still I'll keep 1 better because it is neutral. 4 is charged. So 4 is behind 1. 1 and 4. In 4, octet of all the involved atoms is complete. Don't be bothered that there is plus on oxygen. Okay. plus on an oxygen with complete octet is very, very stable. We do not consider as positive charge on an electronegative atom type thing. Coming to others, if we talk for others, this is going to be very, very unstable. First, the charge polarization, distance to he, bond is less. And to add further, second period elements, when have negative at the adjacent atom, they have that peroxide repulsion, peroxide type repulsion. Okay, not exactly peroxide, but peroxide type repulsion. And this increases the potential energy. So 2 is going to be a bad thing. Okay, is that clear? Now coming to third and this one. They are both polarized structures. But in one, the distance between the opposite charges is less and distance between the opposite charges is more. So 5 is more stable than 3 than 2. Plus on adjacent atom is still stable to this second period lone pair having atom. But minus was repulsive. So order of stability is 1, 4, 5, 3 and then 2. Is that okay? This is how you compare the relative stability of various resonating structures. Moving further, yes, please, if possible for you, take a screenshot of this particular page. Okay, this could be asked in any possible exam. I'm not saying just any fix. Now you take screenshot. I think everything is coming on screen. So what I want to say is that hybridization of atoms participating in resonance is not always sp2. This is a very, very big misconception that always it is sp2. No, that is not possible, that such a thing that always sp2 is there. Okay, the part which will participate in resonance will ultimately come parallel to this. For that need not to be perfectly sp2. See, as I have referred, as I have taken from exact sources and writing the sources, not like I'm saying by myself. In NCRT, if you go to subtopic 11.3, where alcohol phenol ether structures are compared, you will see this bond angle, that it is 109 degrees. Okay, that is to be noted. It is not at all 120. If it was 120, you could have taken sp2. COH, this bond angle is given to be 109. If you go to carry, there is a book for organic carry. On its page number 912, this thing is mentioned. See, if in methylamine, here I have written proper structures also, methylamine. What they're saying, that if there was a planarity, then if I consider an angle between CH3N and an angle bisector of HNH here, if I consider this angle, and if this was planar, this angle should have been 180. Then only I could have said that this particular, what should I say, thing is planar. But what is observed, this angle is found to be 125 degrees centigrade. So definitely it is not at all planar sp3. So you will say कि यहाँ तो resonance है भी नहीं, fine. But by the same logic, if you will come here, this angle is also 142.5, not 180. If it was 180, then you could have said that this nitrogen is sp3, and the author clearly mentions that nitrogen of aniline is sp3. Whereas for amide, it is found that this angle bisector के साथ जो है is 120. So in case of amides, nitrogen is coming to sp2. These are the exact cutting from the carry, and this is explained here. Similar is the observation with formic acid. See, phenol oxygen is sp3, but formic acid, this oxygen is sp2. Okay, So please remember phenol, aniline, these nitrogen oxygen are not sp2. Okay. This is a very, very common misconception that everything that participate in resonance is always sp3, is always sp2, which is certainly not correct. So coming back to next point, which of the molecule is least resonance stabilized? This was 2017 question. Now see, least resonance stabilized. As I told you, something cross conjugation, continuous. You can see continuous conjugation. Very well. You can see again here continuous conjugation. Resonance, badhiya hai. This is king of aromaticity, benzene. Only here, see, this is sp3 carbon breaking the continuous possibility. There is a cross possibility. Okay, so answer was 3. That 3 is the one which is more stable. Sorry, which is least resonance stabilized, less stable than the others. 1, 2, and 4 are more stable. Okay. Next, we go to steric inhibition of resonance. Now, as we have seen, the part which has to participate in resonance should be planar. Here, if I see, if the benzene has 3 groups present continuously on it, see 1, 2, 3, G1, G2, G3. Now what happens first? The inhibition always happens for G2. Less effect on G1, 3. I will never say no effect on G1, G3. That is a wrong statement. There is some effect, there is some discomfort, and it also has some effect. But the maximum effect comes to central one, G2, which practically rotates to perpendicular plane. Okay, it is no more planar. It rotates to perpendicular plane, and thus its resonance. See, if it was planar with benzene, its p orbital were like this, parallel. But if it rotates to benzene, say perpendicular, then its p orbitals are now perpendicular and the overlap fails. So G2 suffers SIR. Now the point is, this is very, very specific to group behavior. If these groups are anyone from this list, the bulky, the big one, which will have the steric collision, acid, SO3H, NO2, okay, this type of alkene. Now, what do I want to say is this. From here, it is connected to the benzene. That is what. Like this, if benzene itself, iodine, bromine, ester, amide, etc., any of these, okay, if these are the groups, all, any, I would say G1, G2, G3, all 3 are from this list. They may be same, they may be different. That is fine. Then whichever group is present in the center will suffer SIR, will suffer steric inhibition of resonance. In short, its resonance with the group will be stopped. So it will behave normal as expected by localized bonding. Now, if G1 and G2 are from this list, okay, which list? It could be alkyl. G1 and G3 could be alkyl, and G2 is from this above list. Then also G2 will suffer SIR. Now I cannot place this R in this thing because G2 can never be R and have SIR because it never has resonance. For inhibition of the resonance, there has to be first resonance. You got my point? So therefore, I have to place this R outside this list. Is it fine? Right? Moving to next, hyperconjugation. Sigma bond resonance. It is also known as sigma bond resonance, Baker-Nathan effect, or no bond resonance. Baker-Nathan effect in the name of the scientist. Okay, sigma bond resonance because sigma bonds now are involved. Till resonance we were talking, no, you are not allowed to move sigma bond. Now we are allowed. And some structures, there will be total loss of certain bonds. So no bond resonance भी इसका नाम है. It is resonance of sigma bonds and is a stabilizing phenomena. Different types of hyperconjugation could be. This is also a stabilizing phenomena. इसमें भी वैसे ही like the resonance energy thing that we discussed, same factor is applicable here also. Okay. On this, there was a question, advanced as well as in mains 21. I'll cover it in later slides. Let's do. First, in case of alkenes, this will be more clear once I write the resonating structure or a hyperconjugative structure for any alkene. And in fact, what all we can study in this resonance. See, this is my alkene propene. If this type of stabilizing phenomena in which you can see this H plus is gone. Gone and not like behaving as an acid, but the sigma bond is no more there. So no bond, there is a condition of no bond. But there are different hydrogens. I have CH2. So there is a possibility that once I have this H bonded and some other H is gone and then this H is gone, right? CH2 minus CH double bond C, H, H and H plus. So this type of resonance, in this what is happening? In this sigma and pi bond is having resonance, right? Here there is sigma and sp2 orbitals are involved. That is sometimes said. Though this is not very appropriate because we are not using sp2 orbitals for overlap. This is an unhybridized orbital. So use sigma and p orbital. Sigma and pi star. Yes, because pi orbital is having this electron pair and this sigma bond is giving its electron to this CH. So it will accept in its pi star orbital only. Is that appropriate? Sigma and pi star. In carbocations, if we talk of carbocations, let us draw some example of carbocation. Smallest system B, if I take, I'll take ethyl carbocation. So CH2 positive. If I start drawing resonance, see, I can call it resonance. It is similar effect. This H is gone. Then this H is gone. Okay, and now this last H I have to remove, say, this H is gone. So there were total of 3 alpha H, 1, 2, and 3. As a result, we got 3 hyperconjugative structure for this carbocation. But in all of them, which orbitals are involved? See, sigma and this plus is acting as a empty p orbital. Which orbital is involved? So you will say empty p orbital is involved. Okay, this is something which students are usually confused with. So I'm going quite slow here. Okay, so in alkenes, what you find? Correct statements are sigma and p, sigma and pi star. In carbocations, sigma and empty p. Now let us go to radicals. So if I talk of radicals where they are having sigma and p, let us draw. Same way like carbocation, I will draw ethyl. Now, but this electron is in half-filled p orbital. Half-filled p orbital, H dot is removed. Correct? So, it is sigma with half-filled p orbital, but ultimately it is a p orbital. So, sigma and p overlap is there. And similarly, you can get 2 more, this hydrogen and this hydrogen, that is why. In reverse hyperconjugation, let us talk of reverse hyperconjugation which is also referred as minus H, right? Because hyperconjugation can be of two types. One in which the system is giving electrons, like here, and one where it is taking electrons. We are just about to draw reverse hyperconjugation. So let us draw. It is found in such systems where three halogens are attached. So chlorine is participating, but as a result, you can see this chlorine is becoming minus, and this is electron depletion. So what this group CCl3 is doing, attracting electrons towards itself. And same way, I will continue with like this plus I'll keep here. And inside this, there could be resonating structures. That is there. But अभी मैं in chlorines की बात कर रही हूँ. So another chlorine is gone. And then another chlorine will be gone. Like this. Okay. So these are reverse hyperconjugation. Now here what is happening? This pi and this sigma is participating. So you can say it is a sigma pi overlap. But to be more exact, it is this pi bonding is overlapping with this CCl sigma anti-bonding. Then we have the better representation of reverse hyperconjugation, that it is an overlap of pi with sigma star orbital of CCl bond. Okay, so these are different types of hyperconjugation. Coming to this, that how it was asked in J. Chalo dekhte hain. What type of overlap is there in ethyl carbocation? See, this type of question was asked. And I think all of you will agree now that it is sp3 orbital, this one, with empty p orbital, or you can have sigma with empty p orbital. That was the answer. Okay, this was the answer. So let me remove this and keep it one side. Take. Moving to this. This was in J 2008. Hyperconjugation involves overlap of falling orbitals. So you can see sigma sigma. No, there was no sigma sigma. There was no pp. There was no pi pi. It is a sigma and p orbital. See, sigma and p orbital overlap. This was asked in advance. Okay, so this concept was asked in both mains as well as advance. A similar question, this total number of structures showing hyperconjugation involving CH bonds. Now, very clearly mentioned involving CH bonds. You don't have to take this structure for the following carbocation. How you will do? You will simply take, okay, isko le rahe. So you have to take alpha positions and marked. Whether there is alpha hydrogen, excuse me, or alpha deuterium, both are participating in resonance. So I have 9 alpha hydrogens. So there will be 9 hyperconjugative structures. Okay. Yes, I said ki you can have deuterium also. In this question, we are having CH. But if it is asked, deuterium will participate in hyperconjugation, though the effect of hyperconjugation with hydrogen is more pronounced, is better than with deuterium. Okay, so this was the question. And number of hyperconjugative structure is simply number of alpha H to C plus or to C double bond C or to C dot. Similar question was asked in 2011 advanced. This was the question asked in 2011 advanced. Total number of contributing structures showing hyperconjugation involving CH bond. So we'll encircle this alpha 1, alpha 2, alpha 3. Here you can see there is one hydrogen. So 1. Here it is 2 hydrogen. Here I have 3 hydrogen. So total is coming 3, 4, 5, 6, 6 sulfide. So you'll simply say number of contributing structures for this will be 6. Okay. So after these electronic effects, let us move to aromaticity. It is also a stabilizing phenomenon. For molecule to be aromatic, it should follow planarity, cyclic structure with continuous resonance, and should follow Huckel's rule of aromaticity. Huckel's rule of aromaticity is 4n plus 2 should be equal to number of pi electrons participating in resonance, not like number of pi electrons in the entire molecule. हमें उससे मतलब नहीं है. We are only bothered about the electrons participating in resonance. Okay. So number of pi electrons participating in resonance, and on solving this, n key value should come a non-negative integer. 0, 1, 2, 3, 4, like that. Okay. So for like benzene, we have 4n plus 2 equal to 6, n equal to 1. Fine. For this structure, I'll solve. N is coming half. And we said this n should come non-negative integral value. So this is not aromatic. Okay. Now see here, it is not aromatic because you have a sp3 carbon involved. Clear? So this is how it should be. Yes, in case of polycyclic molecules, how to apply cyclic molecules, count only peripheral pi electrons. Okay, you have to count only peripheral pi electrons if you want to talk of polycyclic. So what does it really mean? Pi electrons or peripheral carbons. That is also usually working. Peripheral carbons. For neutral structures it works, not always. For neutral structures. Okay? This is main, this is an abbreviated version. So if I have, say, naphthalene, I will have its one resonating structure like this. So I'll count peripheral pi electrons. Peripheral is circumferential, or I can say on the boundary. So 1, 2, each bond will have 2 electrons. 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you will equate 4n plus 2 equal to 10, n equal to 2. So it is aromatic. Okay. Going to next molecule. If we are asked for anthracene. Similarly, I will see if there is any resonating structure on periphery, where everything will be on periphery. Yes, like this. But every time it might not be possible for you to calculate like this. So I have said this thing, I'll explain. 1, 2, 3, 4, 5, 6, 7. 7 pi electrons. So 7 pi bonds. So 7 to the 14. So 14 pi electrons. So n is coming 3, again aromatic. As I said, you can go by peripheral carbons. See, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So actually each carbon is contributing 1 electron. So peripheral carbon on the peripheral pi electron cloud, their contribution is same. So that is why 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So same thing. Okay. Moving further on the same point, you can solve this one and check the structure in which all bonds are on periphery. This one. For this, again, you will have 4n plus 2 equal to 14, N equal to 3, aromatic. Okay. Now, for structures like this, when I can have something which is like in the center, that entirely depends this type. See, my conjugation is broken, right? I can put a bond here. Sorry, I can put a bond now here to have that conjugation. See? So here you have to be careful. Here, your peripheral setting may or may not be. Oh, I have left something here also. This. Okay, then this. Then it is this and this. Now it is completely drawn. Correct. Okay. So see, this is complete benzene. This is complete benzene sort of. And these are this. So if I count the peripheral bonds, 1, 2, 3, 4, 5, 6. Okay. So 4n plus 2 equal to 6. So 4n equal to 4, n equal to 1. Is that clear? See? Now, if you go by the number of carbon, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I wrote here wrong. I counted 6 electrons. So it should be 12, 6 bonds. So there should be 12 electrons. So that is what I wanted to say, that you cannot go by. So it is not a 4n plus 2 system. Right? So n is coming fraction by that logic, 10 by 4. Now you may say that I can draw a different resonating structure, and then yes, you can, but how in the exam you will conclude that the resonating structure drawn is inappropriate or appropriate? That is the problem with this type when some carbons are embedded inside. So if you count the peripheral carbon, it is coming 14, because whichever resonating structure you draw, this corner carbon will have its electron on periphery ultimately always, right? So n equal to 3. Yes, this is an aromatic system, but you have to calculate peripheral carbon. You can have peripheral pi bond system, but that depends on the resonating structure which is taken into consideration. If it is something else, say like this, okay, you may have a setting of 4n pi electron, say bhi answer aa jaye. There is a possibility. Let us calculate. 1, 2, 3, 4, 5, 6, 7. See here, peripheral pi bonds. Pi bond is 7. So pi electron 14. So now this resonating structure, if they have given, you will land the correct answer. This resonating structure, you may get confused and land to inappropriate. So that is why I'm saying in neutral, it is better to count the peripheral carbons and go for the calculation of 4n plus 2. That is faster, easier, and safer. Okay. And this is because aromaticity is a chemical condition in which the stable electron cloud is there. That is achieved in that at periphery. See, this was a 2017 question. As I have said, that any part which is satisfying should be used, but this one. Okay, I'll come to this question after anti-aromaticity. Let's wait first. We'll come back to this question. Anti-aromaticity. It is also a destabilizing phenomena. Okay, rather no need for also. It is a destabilizing phenomena. For molecule to be anti-aromatic, it should be planar, cyclic with continuous resonance, should follow Huckel's rule of anti-aromaticity, in which 4n is the number of pi electrons and n should be some positive integer value. And so 0 is excluded. System like this, you will have 4 electrons, n equal to 1. System like this, 4 electrons. Okay, fine. So it is a destabilizing phenomena and you can have such representations. Then comes non-aromatic. Non-aromatic is for whatever reason, if a molecule could not be aromatic, could not be anti-aromatic, then just dump it like a dustbin into non-aromatic class. Okay, NON, non-aromatic. It means it is neither aromatic nor anti-aromatic. But if the question is says not aromatic, then not aromatic word includes both anti and non-aromatic. Okay, whereas non-aromatic includes only non-aromatic. Only non. So read the question carefully, whether they are asking non-aromatic or they are asking not aromatic. Okay. So for whatever reason I was saying, take care for molecules like this. Yes, there is breakage of conjugation. Entire molecule is not planar. But if a part of molecule is having aromatic cloud, you will regard entire molecule to be aromatic. Like here, toluene, this part is having aromatic cloud. We are not bothered about CH3, so this is aromatic. So is this. Okay. And if sometimes due to whatever reasons, molecules becomes non-planar, like this one, which is extremely famous because it is tub shaped, right? Cyclo octa tetraene, this tub shaped. Molecule is like this. Cyclooctatetraene is a tub-shaped molecule. So it appears to be anti-aromatic on paper, but it is non-planar. So for whatever reason, if a molecule is non-planar, it is going to be non-aromatic. That is a fixed rule to follow. Okay? In this process, you may sometimes come across species like, see this annulenes. I'm talking of annulenes. Annulenes are monocyclic hydrocarbon system with conjugate pi bonds like this. This is 10 annuline. By simple counting of electron, it should be aromatic. It is a twin, almost a twin brother of naphthalene. But no, it is non-planar and so non-aromatic. Okay, here there is hydrogen. So due to repulsion of these hydrogen, non-planar due to trans-annular repulsion. Okay, then next comes the 12 annuline. Let us count the carbon. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Like this. Okay. So this is expected to be anti-aromatic if you don't know the structure. But again, it is non-planar and non-aromatic. Non-planar and non-aromatic. Then we goes to, similarly, you can just keep on going, say 14 annuline. I will not draw the structure now, I'll simply write, is non-aromatic. But bridged 14, bridged 10 and 14 दोनों के लिए बात valid है. So let me write properly. Bridged 10 aniline or 14 aniline are aromatic. Okay, what I want to say by bridge, for example, if this some CH2 is there, okay, so now it will not have that non-planar CH2. Here it could be CH2, oxygen, nitrogen, etc., which is bridging sulfur, कुछ भी हो सकता है, ठीक? So they are aromatic. And similarly, dihydro-14-aniline is slightly non-planar but aromatic. ओके, सो ये याद रखिए, ये सब एरोमेटिक की कैटेगरी में आते हैं, ठीक? These are all called aromatic compounds. And after discussing all this, if I want to conclude stability, then always remember, सबसे ज्यादा stability किसकी है? Aromatic. Then comes the non-aromatic. And then comes the anti-aromatic. That is how the order is. If in any reaction, compound is coming from anti-non-aromatic to aromatic, reaction will be very, very favorable. But if something is going from aromatic or non-aromatic to anti-aromatic, you will say, no, this reaction will not take place. Is that clear? Let me take one example. For example, if this is there and say this give addition of HCl, you will have this carbocation formed. And you will write Cl minus like this. It will remain as species charged, as like this ionic. You will report this, not, you will not report this. Okay? Never, I should, how to emphatically say never. Never report this. Why? Because this you are reporting as non-aromatic. And this you are reporting as aromatic. Always leave your answer, even it is in form of ions, if the compound is aromatic. Okay, so now coming back to where we left questions. So among the following, the number of aromatic compound is, now I have already discussed, this is tub-shaped, non-planar, so it is non-aromatic. Here, 1, 2, 3, 4, anti-aromatic, aromatic. This is not a continuous cloud, non-aromatic. Tropelium ion, very famous. Tropelium ion. And 1, 2, 3, 4, 5, 6. So this is aromatic. This is anti-aromatic. 1, 2, 3, 4, 5, 6, aromatic. And this is called cyclopentadienyl anion. Right? This is called cyclopentadienyl anion. Such aromatic species which are charged are called quasi aromatic. क्या कहते हैं इन्हें? Quasi aromatic. Coming to this, see, yes, there are sp3, but again, this is aromatic. So you will report this as aromatic. This I have just solved for you how to take peripheral aromatic. So let us conclude how many we got as aromatic. Number of aromatic compound, 1. Of course, this one, 2, 3, 4, and 5. So Answer for this 2017 JEE advanced question is 5. So take care, even if one aromatic cloud is formed, you take that compound to be aromatic. Okay, and sometimes this generation of aromaticity is the reason for compounds to be polarized. I want to comment on azulene, which is a 5 and 7 member ring combination like this. So if you'll draw its resonating structures, a 7 member ring will be polarized when, or will be having its individual aromatic cloud when, if I do it this way, minus, okay, like this. Clear? So this is an independent aromatic cloud. This is an independent aromatic cloud. So basically it is 4n plus 2 equal to 10 naphthalene. It is an isomer of naphthalene. But in its hybrid, what we found is a very strong dipole moment from directed from 7-member ring to 5-member ring. And why is it there? Because of this individual aromatic character generated in these two rings. Okay, individual aromatic character generated gives more stability. Which of the following molecule is pure in pure form is unstable? So this is your anti-aromatic system. You polarize it, make it plus, make it minus, and you can check this is anti-aromatic cloud. 1, 2, 3, 4. Again anti-aromatic cloud. Okay, non-aromatic cloud. And if I polarize this, this is an aromatic cloud. So unstable at room temperature is anti-aromatic. So B and C are your answer. Is that clear? Take. So this is non-aromatic. Done. We have done this page. We have done this. I wanted to talk of some polycyclic, where we did that polycyclic thing. Okay. So we did somewhere polycyclic thing, na? So in polybenzenoid systems. Point number 1, total resonance energy increases with increase in number of pi electrons participating in resonance. That is fixed. So you will have more resonance energy of anthracene, then naphthalene, and then benzene. Okay, this is fixed. But stability of the molecule is decided by resonance energy per ring for the molecule. For the molecule. Okay. So here, if I talk of stability, the order is just reverse. If I replicate it here, then the order is this. Per ring resonance energy is like this. Okay. And per ring resonance energy is higher when in different RS we have more number of independent बेंजीन क्लाउड्स। ये ध्यान रखें आप। मतलब फॉर एग्जाम्पल इफ आई टॉक ऑफ दिस, सी इन एंथ्रोसीन I can have best of best two rings. See, this is one cloud generated, this is one cloud. So I have two benzene rings, right? That is max I can have. If I go to phenanthrene, this is my phenanthrene. See, I am having all three as independent benzene. Such a resonance structure is possible. Okay, this is possible. So if I'm saying this will have more resonance energy, though the number of pi electrons are same. Okay, but here I am having independent these pi electrons in generating a resonance of benzene cloud. Is that clear? That is how you will calculate per ring or resonance energy. One more thing. Per ring, you can do one more thing. Let me come here. Let me put pi electron here. So total pi electron resonating is how much? 10 and distributed into 2 electrons. So 5 electron per ring resonance. Here I have 6 electron per ring resonating. And here I have 7 pi bond, 14 electrons. So 14 by 3 electrons per ring. More this value is, more will be the per ring stability. Okay, so please take care of this factor. If possible, take a screenshot of this page. It will help you till phase 3. Okay, so moving further, which of the following compound is not aromatic? Now see clearly not. This was asked in mains 2019. Aromatic, aromatic, aromatic. This is anti-aromatic. Answer is 3. And I guess it was 3. It is anti-aromatic. And similar questions were repeated in 2019, 2020, 21, 22 onwards, almost every year. Okay. So that was about the electronic effects. But in electronic effect, I need to add one electromagnetic effect reading that I'll add. Coming to electrophiles. So electron loving species are called electrophiles. They are always Lewis base. Remember, they should be capable of accepting an electron pair. Ultimately, electron loving species should be capable of accepting an electron. So any carbocation, okay, you can have BCl3, you can have BF3, AlCl3, electron loving species. I can even call aldehydes because they are electrophilic in nature. You can have ketones, cyanides. These are all electrophiles. They want electrons to attack on them. Okay, these are all electrophiles. Yes, Jaya, you rose your hand. Is there any doubt you want to ask? Let me check my speaker is on. Yes, it is. So unmute yourself, Jaya, and ask. I don't find anyone. Someone just rose hand. Okay. Another person, Raja. Yeah, please unmute yourself and ask.
Ma'am, is it electrophile Lewis base or Lewis acid?
Lewis acid, of course. Yeah. Okay. And anyone
Okay, got my
else,
doubt.
please?
Thank you.
One more hand was there. Same thing. Yes, it is acid bitter. No one? Okay, Raja, please lower your hand. Or I did, I guess. Coming back to anyone else? No one? Okay, moving further. So these are electrophiles. Then similarly, there could be nucleus loving species. So they will be Lewis base, right? They will be positive charge loving species. Loving species. So there are so many, again, CH3 minus, ammonia, alcohols with their lone pair. है We can have this amines, entire amines. These are all nucleus loving species. Even benzene is acting as a nucleophile because electrophiles attack on it. So this is a nucleophile. You can have so many HO minus, halides, ammonia hai to NH2 minus is there, RO minus is there, RCO minus is there. I'll just rest the case with etc. Okay, so that was about nucleophile. As I said that please don't leave the class before one NCRT reading I want to add. Let me add. I don't know whether you are able to see the screen or okay, you are seeing that. Let me open the NCRT which I want you to read in your working sessions. Compulsorily read for both mains and advanced. Okay, just go through that, and if possible please read it before your Saturday Sunday exams. It is good to have at least 2 to 3 times reading for NCRT before final exams. So I guess I'm there, but I have to change the sharing. A second. Let me share the screen. Are you able to see the NCRT, bacha? Yes? Okay. I think it is there. So in this chapter, Organic Chemistry, Some Basic Principles and Techniques, in this chapter, let's go to a little further, this IUPAC. Here, fundamental concepts. Okay, when they are explaining these fundamental concepts, you have to read the entire chapter, certainly. That is there. Please read this ekdam meticulously, correctly, taking reagent, intermediate product, whatever they are saying, a sequential account of each step, describing detail of electron movement, energetics during bond cleavage and bond formation, and the rate of transformation of reaction into products is referred to as a reaction mechanism. Fine. These are order of stability and everything that is in NCRT. Kindly read it as many times as possible before your advance, or better before your mains. And ideally, it should be read at least 3 times, all 4 volumes, physical, inorganic, organic. So this is heterolytic, homolytic bond fission. Okay, this entire thing. Now, what you can continue with this. Now, electromeric effect is best given only here. In no other good book it is given. So that is why I wanted to point out. Please read all this nucleophile, and a reagent that brings an electron pair to the reactive site is called a nucleophile. And please see, it is wanting an electron pair, not a single electron. That is something to be noted. Anna, you cannot have a something that is attacking on a nucleus with a single electron. You cannot call it as a nucleophile. It has to be a pair of electron. Okay? A reagent that takes away an electron pair. Again, something that takes away an electron pair. A single electron is not to be considered. Then it is called electrophilic or electrophile. These all points, na, small meticulous points can cause you to do errors. Coming to this electron movement, we have covered this part today. So please read it by tomorrow if possible. That would be best. So how they have explained, because these type of questions we can expect in mains. Okay, so this you go. Electron displacement effects. Now here you will find somewhere electromeric effect defined. So inductive effect is there. Electron withdrawing or donating, and these groups are there. Let's move. I am primarily concerned for the word electromeric. Resonance is there. Okay, fine. Find the word electromeric and let me just reach there. This is what I want you to read. It is a temporary effect. The organic compound having a multiple bond shows this effect in the presence of an attacking species. When something attacks, then this effect is shown. So it is a temporary. When that thing is gone, see, alkene pe H plus is coming, right? So this was a neutral bond, but when H plus approaches it, it generates a positive charge. So it is in presence of this attacking reagent. It is defined as a complete transfer of a shared pair of pi electron to one of the atoms joined by a multiple bond on the demand of an attacking reagent, and the effect is annulled, matlab removed. As soon as the attacking reagent is removed, it is represented by capital E, and the shifting of electron is showed by such curved arrows. So it is again plus E, because here H plus is giving us a plus E. You can have minus E. Cyanide when coming, then due to repulsion, the charges created are of different type, no? Minus. This is again a very important line. See, when inductive and electromagnetic effect operate in opposite direction, please read it carefully. Which is dominating? The electromagnetic effect dominates. Is that clear? When inductive and electromagnetic effect operate in opposite direction, then electromagnetic effect dominates. This type of reading, I request you all to please read it by tomorrow till this thing in hyperconjugation. I cannot mention by page wise because my NCRT might be some different edition, yours might be different. So this chapter, yes, Saharsha, just wait. I'll ask you to unmute. Just wait, huh? So all these type of reading is a must, and here also solve these questions. Okay, these questions could be any day converted to like multi-correct ones, and they can ask us. Okay, so please orient yourself compulsory to NCRT reading. Yes, Saharsha, please unmute yourself and ask beta. Is there anyone? Saharsha was there raising hand. I saw. Okay. So I assume either they are Saharsha Chakilam asked to unmute. Okay. Yes, Saharsha, you have raised your hand, but you are not asking.
Excuse me, ma'am.
Ah, beta, be louder. Yes, speak.
Excuse me, ma'am.
Yes. Tell. I'm listening.
Ma'am, do we have these classes every day?
That will be like 4 to 5 days a week.
Ma'am, do we have these classes every
Yes,
day?
these will be like every day, and the schedule will be shared by central office to your center principal or vice principal. Some management will be communicated. These classes will be at least 4 to 5 days a week. Okay, excluding Saturdays when you will be preparing for your following exams. Okay. Is that it, Saharsha? Akhil, you also rose your hand. Is there anything? Ibrahim? Yes, Ibrahim. Yes, unmute yourself and ask. Akhil and Ibrahim, one by one, you go ahead, both of you. Okay.
Ma'am, if there are two rings joined by a bridge carbon, one
Ibrahim,
is aromatic and the other is anti-aromatic.
your voice broke. I could not listen the entire question. Can you please repeat?
Ma'am, if there were two rings and they were joined by a bridge carbon,
Two rings which are joined by bridge carbon. That is what I could see here. Is it?
one is aromatic and the other is anti-aromatic, what would be the resultant compound?
I cannot answer something that is very imaginary for me. If you could share some structure or ask me to draw some structure, because chemistry is very much what actually things exist. So it is
So,
difficult for me to answer until unless I have a actual structure. That is it actually possible even that such type of structure exists? What I could think of you answering or questioning, जो मेरे को दिमाग में आ रहा है, but I don't know whether my screen is shared or not. So let me share and then we'll try to explain. जो मुझे समझ आ रहा है question, what you are asking. Let me go to last page. मुझे लग रहा है इब्राहिम यू आर आस्किंग विथ कंसर्न टू व्हेन benzynes dimerize. Is it in context to such type of structures, Ibrahim? Please tell Ibrahim, unmute.
Ma'am, no, like since if we attach a benzene ring with a methane group, it will be aromatic.
Yes, certainly it will be
But
aromatic.
to the methane group, instead of CH3, if it was CH2 and some other ring which was anti-aromatic.
So you see now this example, this is I think in support of your question. See anti-aromatic ring in the center.
Yes, ma'am.
Is this satisfying your question? Then we
Yes,
regard
ma'am.
it as overall aromatic compound.
Okay, ma'am.
Okay, and we say that of course as compared to two independent benzenes, this will have less resonance energy because in a center there is a possibility of anti-aromatic cloud.